Now, what we're going to discuss today is a little bit more about monoidal functors, or as we like to call them, monads. Now, let's do a very short recap. So we know that a functor f is a generic type and a map f function that injects a function ab into a function fa fb. And for the functor to be monoidal, we also expect two additional operators. Unit, which in some languages is also called return, which is again a generic function, takes as input a value, let's call it x, of type A. As a matter of fact, this is id of A, and returns an instance of f of A. And finally, this is a sort of constructor, and finally join of A, or in some cases also called flatten, which takes as input an instance of our functor with a nested instance of the functor and flattens it into a single instance of the functor. And if these things, unit and join, can respect some specific operations, then we say that functor f is also a monoid or a monoidal functor, and as such it's also a monad. In the last lecture we've seen some very simple functors, and today we're going to, some very simple monads. Today we're going to look at perhaps the first actually useful one, the option monad. The option monad is useful, and its usefulness is also, you could say, proven by the fact that option is available in most mainstream programming languages. Let's start with the definition. An option of A, here is already the first bit of the functorial part of option. Option of A is either of two things. The simplest instance of an option, as we know, is just empty or nothing. And if the option is not empty, then it has some value of type A. Let's begin by defining the map function. The map function over an option is generic in A and B, and it embeds a function from A to B into a function from option of A into option of B. And there's no way around it. We really have to define map option. Okay, there are ways around everything, but for now let us simply state that the functoriality of option is not something that we really get for free, at least in this context. So the functoriality of our data structures is something that we must be willing to specify by hand. So now I have to create this function of option of A into option of B starting from f. Let's begin by saying that this function will take x as input, and the type of this x is option of A, and from x and f I have to be able to generate an option of B. Over the x there is not really much we can properly do, so I can check what we know about the kind, and if the kind is none, our kind of done already, so I could go and create kind is none, because that's what we're supposed to give. Otherwise, kind is sum, and the value is going to be, we call f, and what we give is x.value. It's always handy to define constructors for these two, for the various shapes that a generic type can assume. So none of A, which returns option of A, simply gives us kind none, whereas similarly, we'll look at it in a second. It is happy. Okay, good. And otherwise sum, which embeds x of type A into, again, an option of A, returns kind sum, and the value becomes x. Okay, we're reasonably happy. So now if the kind is none, we can simply say none, and otherwise we can call sum of f over x.value. Okay, looks a bit prettier. Also notice, and this is kind of funny, that this looks a lot this looks a lot like one of the things, like the next thing we need, because that's unit. We know that unit, whether we say x is id of a or x is a, that's the very same, because the simplest functor of all, where everything is the identity, also the simplest monad is the identity monad. And indeed, we could say that id of a, being the same as a, could also be added to sum. Now sum really is the constructor that embeds a value of type a, whatever it is, into the simplest possible option that manages to contain it. You can even say that unit is simply sum of x. I don't know if the language is smart enough. I don't think so, actually. No. Also not like this. Oh yes, that's awesome, actually. So I can just rename the symbol and it knows that unit is a generic function that takes x as input. Okay, that's brilliant. And now the last bit we need is join. So join is a generic function, takes as input an option of a and gives us a single option of a back. And well, similarly to one and to unit slash sum and map option, these are some of the things that we really need to specify manually somehow. So left or right, we have to specify these things manually. And obviously you could imagine that if you have defined already some functors or monads, and you know how they are functors or monads, and you compose them, that you might reuse that. Even though for monads that's not so automatic, but that's very advanced, and for all practical purposes, let's simply assume that when we state a new monad, unless it's a very clear composition and we can reuse some parts of the composition of existing functors and monads, we have to simply be verbose and specify in what sense the monad is a monad by defining join, unit, and map by hand. Okay, so now what can we do? Well, for join, we literally have nothing but x. So, well, if kind is none, yeah, there's no more data, so let's simply give none back. Otherwise, well, we have a value, oops, and, well, again, if value is none, well, we had a bit of hope, but the hope is quickly lost, because the content, there's some content, but the content itself is empty. And finally, well, what do we have here? Oh, we have an option of a, so we're actually kind of done. Also, well, you could notice that if the kind, well, we could do this in a slightly more verbose way, so we could state that we rebuild a new option, but because the option is meant to be immutable, then you could almost say that there is only one instance of none. So here we could simply return x.value. And here, instead of rebuilding sum of x.value.value, which is the very same as x.value, well, we have x.value, which means that this whole conditional might be skipped entirely, because, well, there you go, both sides return x.value, so let's just return x. Oops, I don't know where that came from. So we can simply return x.value right away. So now we have map option, unit, and join, so we are pretty comfortable in stating that map option is a monad. That's actually lovely. But we also stated that a monad has an operator that comes for free, which is the then operator, or bind. And then, well, it takes as input implicitly an f of a. I'm going to simply say that it's, let's call it this, because we actually have this possibility. And we have a continuation that goes from to simplify the syntax a bit, from f of a into, oh sorry, from a, which is the content of this, into f of b, of which we might get a multiple of, and finally we return f of b. And the idea of bind slash then is that we're going to extract, run, do something to get from f of a to one or more a's. For each one of those, might be 0, might be 1, might be a million, we don't know yet, and it doesn't really matter. We extract an f of b, and for every f of b, again, we might have 0, 1, 50, we combine them into the final f of b. Let's define this. Let's define this as then option takes as input. Now, it's a generic function, takes as input. this, which is an option of a, the continuation k, which is a function from a into option of b, and finally returns an option of b. Let's do the evil compiler leave me alone trick for a second. So how many a's can we find here? 0 or 1. And it means that we get 0 or 1 options of b in return. And we have to sort of merge them. Now, let's try this. So we have b, we have k. And we have map option. So there we go. Let's use map option, because map option we could give it our function f, our function k, and look at temp1. Now temp1 is smart enough to see, okay, so it goes from, so we gave it something and goes from a into option of b, and it's put option around the parameter and the result. So now instead of a to option of b, we have option of a into option of b. That's very nice. And so temp1 is now hungry. It says, no, please give me an option of a. Okay, cool. So we just call it. We just call it with the option of a that we have, because we have p. And now temp1 is an option of b that we can simply join. And what we have now is a simple option of b. That's actually, well, pretty easy. Now, if I'm not mistaken, we could also simply say that when this is done, then we join, and we apply this. I'm not going to waste more than 5 seconds on this. Oh, and we actually do get lucky. That's very nice. So it's kind of the same. So this is a way of saying, okay, map option of k, and when whatever result this gives us, which is the option of b, then please join it right away, and then to this we give p. And if we play around with curling a little bit, we might actually simply could get rid of this parameter and this parameter. But in the simplest way, actually, I can show you. If we say that then we want an option of a before we produce the option of b, then this is literally all we need to return. Which is also okay, but the first parameter p is going to disappear because it's going to be this. And then this is actually quite pretty, so let's, you know what, I don't know if this is going to come back and bite me in the ass later, which might very well be, but I'm going to improvise and simply leave it like this because I love it when we make parameters disappear. And the k is very difficult to make disappear because map option is kind of a 2-parameter function, and we really need to put the first parameter in. Okay, so now we have a map option, a unit join, then option, which counts for free because this is always the same for every single monad. It doesn't really matter what option is. If these were list, for example, it would still work, and every option would obviously have to become list, but so you get a gist. So this is for free, then is for free. We don't need to specify it again. So whereas we have to state what join, unit, and map are for a given monoidal functor, then counts for free as long as we have specified those things, which is very nice. And we also know for sure that then is going to make sense in a very strong sense, in a very strong, in a very strongly meaningful way. Okay, now I'm going to add something to the type option, and I'm also going to state that every instance of option is supposed to take as input a then parameter, which looks a lot like this. But not quite. Oops. And gives us an option of b back. Oops, no, that's an arrow. And now obviously, well, none is slightly unhappy because we also have to specify the then value, and then is going to be a function that takes as input. Now let's copy this, let's copy most of this declaration here. Well, it also needs to take this, which is an option of a, returns an option of b, which is so much boilerplate, and finally returns then option of k, which we then apply to this. And well, now it's happy. I mean, horrible verbosity, but and this thing is always the same. I'm just going to be again a bit lazy, just put it here as is. And now our options are our options may enjoy the pleasures of then. In what sense? Now suppose that we now want to define a function, safe division. This function takes as input two values which might exist or not, because I don't know, they came from a source of numbers which is unreliable files or whatever, or the network. And we want to return an option of number. Why? Because if the number that we're going to divide by is 0, then we don't want to run to perform the division. We want to simply return the option of number. And one might say, okay, we have the kind, and if the kind is sum, y.kind is sum, but this is then I could, oh wait a second, and y dot, this is disgusting, dot value is not 0, then I could return sum of x dot value divided by y dot value, and otherwise I could return none. But this is terrible. Why is it terrible? Because I'm not supposed to think about all of these nested details of the internals of what an option looks like. And what if someone comes from the Haskell world and instead of calling it sum and none, use something else like just and none, for example. Just, there you go. Why should I remember this? Also, why all these x dot value, y dot value? No, this is a dependency that we actually don't really want to have. Fortunately, there is no need to do it, because I can say x dot n, and well, this is going to invoke the callback k if there is, for each value xv inside x, which might be 0, and if there is none, then we simply return none right away. Then I can do y dot then and yv. Now here at this point, I have two values, xv and yv, and if x or y, so and this means that both x and y were sums. So now, well, now we can simply check yv. So instead of y dot value, etc., if yv is different from 0, then I simply return xv divided by yv, and otherwise I return none. And you could call, oh, oops. Now let's see if type inference needs a little bit of help. Okay, now let's debug this. Let's help it a bit, and then we'll find out what actually went wrong. Plenty, apparently. Let's try to put number here. No, I don't want to waste this, obviously. Simply put none, and let's check out what error we actually get. So, if you look at the error, it says, obviously that this is a normal lambda, whereas it should be a fun. That's not a big deal. So we can encapsulate this into a fun, or to make this more JavaScript idiomatic, we could even state that here it's not supposed to be a lambda in the declaration of then, but in the proper definition of the operator, so here in the option, it is supposed to be a lambda. Sorry, it is supposed to be one of our funs. So now I have to adjust this signature here. Again, not a big deal, because the fix is super quick. K is let's call it normal lambda, and then when we pass k, then we simply encapsulate it in our wrapped functions, and there we go. Now it's happy. So let's restore our original code. This was really a minor dumb mistake, but these things can happen. We don't even need all of these type annotations, I hope, because the system, the type inference should be smart enough. Also because we've told it that it's an option of number. Let's see if it's smart enough to guess it. It should. And oh no, it isn't. So at least here outside we really should be verbose. And now the nice thing is that because of this uniformity, you can see some monoidal properties of option of number which are inherited by, well, kind of by the fact that both option is a monoid and number is also, well, now this is not really fully monoidal obviously, but it reminds us of the join operator of monoids. it means that we can chain stuff easily. So we could say that we have safe division of, and now I could simply have something that didn't come from the network, sum of 3, and further divided by sum of 0, and this is fully safe and it will not crash at runtime, and it will simply give us none. Well, it gives us none because this guy here gives us none, but in this case, because the sum of 0 here, the second division is not going to make our program crash and burn, which is fine. Safety is always a positive property. Okay, now one last stylistic notice is that option of A is itself a very restrictive variation over another data type, which is either, and either is a powerful data type which is very similar to pairs, as a matter of fact, which can be either left, containing a value of type A, or right, containing a value of type B, and we call either the discriminated union. A discriminated union because you get either A or B, and there is no overlap, nothing falls in between. And let me define a very useful type as well. So now either AB also knows two constructors, and they both look a lot like sum. They're called inl, oops, or left if you want. Takes as input a value of A, is generic in two types, but B is not used, and gives us either of AB, and the kind will be left, and the value will be, as you could imagine, X. And inr, which injects to the right, X has type ID of B, and the only thing we have to adjust is that the kind is right. Now, option is, drum roll, no more and no less than either of unit or A. Most of it already works, but of course now instead of none we have left, and instead of sum we have right. Let me begin by adjusting it here. So we have left again for the construct. Oh no, left, not LFT. Okay, and here we could go the verbose way and say that this is left. No, this is right. No, this is really left. Oh, but obviously we also need to produce a value which has to be unit. And here we could simply say, okay, you are right, and the value is X. That's kind of verbose though. We could reuse the definition, and we could say that in this case for none, then we simply inline nothing, and we embed nothing to the left, and here we embed X to the right, thereby obtaining the composition. And now, and this is what I meant with you sort of get some stuff for free, especially functoriality, if you can prove that your data type, like in this case option, is somehow derived from is derived, sorry, not somehow, is really derived from something that of which we know it's already a functor. And indeed either happens to also have a by map, because we can map both sides. So I'm going to say that we have A into A1 and B into B1. Then we take the left mapping, which goes from A to B, sorry, from A to A1, and the right mapping, which goes from B to B1. And this maps either of AB into either of A1, B1. Now, the input of this is our either AB, the output is either of A1, B1, and what we do now, as you could imagine, if it's left, then we embed to the left. Instead of stating this is none because it's not empty, now we have x dot value is of type A, and it has to become an A1. You can see that it's also suggesting it right away. It's saying, yeah, give me an A1. And how do we get an A1? That's actually quite easy. We call L.f, which expects an A, which we have because that's x.value, and it produces an A1, and otherwise we inr r.f x.value, because x.value here is b, and f is capable of turning the b into a b1, and that b1 we put obviously to the right side of an either. And it's also always nice to notice how smart it is, because it knows here a1, obviously because we give it a value of type a1, but it knows that it has to produce an either of a1 and b1 because that's the result we're supposed to produce. Let's see how smart it is, because it shouldn't need that many annotations, and still it knows that the right one has to be a b1 and here the left one is an a1. Probably because they are supposed to be the same, also probably because we have this annotation, so at some point if we remove annotations it's going to break. I'm going to leave it here nicely verbose as nicely verbose as they are. So now for the map option, how do we map an option? You could imagine that we don't need to do this anymore, because we could simply map the underlying option inside X. We could map it via map either, where, well, the left side is going to stay the same because it goes from unit to unit, so it's going to be the identity. And let me state that the identity function, because I started from an empty file this time, is a function from A to A, which is x goes into x. There you go, we have the identity function. So now for the map option, I have f, which goes from A to B, but you have to realize that well, that f has to be applied to the right side of the either that's inside the option. So without further ado, let's begin with the horrible evil trick, because we're going to have to re-embed the then, because then is inside option but it's not inside either. Now so we have our x, and let's say temp1 is map either, which takes as input, well, two functions. The left side, it's not really going to have to do anything, whereas the right side is going to be f. Now let's see what temp does. It's a function of either unknown a into either unknown b, because from id it has no idea whatsoever what a is supposed to be. But let's give it a hand. Let's say, no, your id of unit, so now it knows that temp1 is a function either unit a into either unit b, which, hey, lo and behold, it's exactly what option of a is supposed to be. And we call this over x. And now temp1 is either of unit b, which is almost what we want. But if I were to state that this is the same as option of b, well, no, it's going to complain because it says property then is missing. And, well, it would be right. Now, so then, it's always the same actually, but I'm simply going to copy it over. And, well, we should have at some point, oh, which one is it? Nope, okay, we need a new line for this. Oh, yes, okay. And why is it unhappy? Because, why are you unhappy? Why are you unhappy? Oh, because well, it goes from B to C. Yes, okay, that's the issue with naming. Yes, okay, there you go. Yeah, because A and B here have inside the definition I had for then have a different meaning than the A and B that have that are defined inside map option. But we really should have something like put then around this around this either, because then is already repeated 3 times. But first let's see if we can just return this in one go. And, well, at least this is not ugly anymore. Almost not ugly. Okay, getting close. And, well, now map option inherits functoriality from either, which again is quite nice. As a last touch, let's try to see if we can embed this then around an either unit of A. So let's say either to option is a generic function in A that takes as input the either, which is an either unit A, and it is supposed to return an option of A. And I'm going to try the easy route because we know that this works already, but instead of calling inl, we simply put x here, and now I should be able to simply say that I have this inl and I want to convert it to option, and well, that's nice. And also for the inr here, and there we go, it's happy, and the very same can be done here, either to option, and we simply call map either, and there we go. Now our code is also prettier and features less repetition. Thanks a lot for listening, guys, and best of luck with your study.